multivariable system, detuning multivariable, systematic detuning. Of multivariable systems, decentralized system, that means, yeah, that means what it means. Okay. Well, so let us say I got a 2 by 2 system, let us take an example, and man, we have drawn this so many times, I am tired drawing it again and again and again. Okay. So, if I have a multivariable system and I am trying to control this guy using a controller, this is my decentralized GC1, and I am trying to control this guy using another controller, this is GC2, and of course, effect on 1 of 1, this is U1, this is Y1, this is U2, this is Y2, effect on 2 of 1, effect on 1 of 2, effect on 2 of 1, yeah, and this is Y1 set point and this is Y2 set point, of course, plus minus negative feedback plus minus, yeah, okay. Let us say this is plus 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 plus. Okay. If I have this kind of a system, then let us just do a mathematical, let us just develop the equations of the relationship between Y1 SP and Y1 Y2 and Y2 SP and Y1 Y2. If I, well, how do we do it? Well, let's do it here. Let's use this space to do it. Okay. Then what I have is Y1 is equal to G11 U1 plus G12 U2, and Y2 is equal to G21 U1 plus G22 U2. In matrix form, I can write Y1 Y2 is equal to G11 G12 G21 G22 U1 U2. This is a representation of the same equation where I am saying y vector is equal to GP process transfer function times U vector, matrix of process transfer function. Okay. Now that we have done this, what is U equal to? You will find that U1 is actually equal to GC1 times E1. That's actually decentralized control. In that, input 1 is moved based only on E1, you do not care about what is happening to error 2, and U2 is moved based only on error 2, independent of what is happening to error 1, which is basically in matrix form saying U1 U2 is equal to GC1 GC2 0 0 E1 E2, and E1 E2 is actually Y1 set point minus Y1, and this is actually Y2 set point minus Y2. So, if I look at this equation, let me call this the controller matrix GC, and that is, I repeat again, the fact that the off diagonal terms in my controller matrix are 0 implies I am doing decentralized control. Okay. So, now what I am saying is that this is equivalent to u vector being equal to GC matrix, which is a decentralized matrix, times y set point minus y, no, this vector. So, well, I substitute for u what I have derived here, and if I substitute for u what I have derived here, maybe we should do it on the next page. Insert new page. So, what I had was y is equal to GP matrix times u, and what I had was u is equal to GC matrix times y set point minus y vectors. When I substitute for u, what I will get is y is equal to GP GC, and please note here that the order of matrix multiplication is important, because matrix multiplication is not commutative, okay, times y set point minus y. Yeah, and if I take the y term to the left hand side, what I will get is identity matrix plus GP GC matrices, this is also a matrix, times y is equal to GP GC matrix times y set point, and therefore, what I will get is y is equal to identity matrix plus GP GC inverse times GP GC, of course, matrix multiplications times y. Remember, for seesaw systems what we had, do you see the analogy? For seesaw systems what we had was y over y set point was actually GP GC, the individual transfer functions, divided by 1 plus GP GC, and so what you actually have is y is equal to 1 plus GP GC inverse times GP GC times y set point. Do you see the analogy? This is for a seesaw system, this is the equation for a multivariable system, but it is the analogy with the seesaw system is pretty clear. Okay. Now, when I am inverting this matrix, so now let me say my multivariable system is y is equal to some matrix G closed, some matrix of transfer functions times y set point, and this matrix of transfer functions G closed loop is actually equal to I plus GP GC inverse times GP. This is what I get. Now, let us look at this matrix which I am inverting. GP GC would, okay. So, let us say I have a 2 by 2 system. If I have a 2 by 2 system, when let us say I got I plus GP GC. So, let us say a 2 by 2 system, for a 2 by 2 systems I plus GP GC would be what? The inverse matrix for that 2 by 2 system that we have would be a 2 by 2 inverse matrix, and this inverse matrix will have 4 terms, 1, 2, 3, 4, and then of course there will be this inverse matrix times GP GC. Okay. This inverse matrix will have as the denominator, in the denominator it will have a term which is common to all the, when you invert matrices, what do? You calculate the cofactors and divide by the determinant of the matrix, right. So, what I have is determinant of this matrix I plus GP GC this determinant is there in the denominator of all the terms. So, there will be something in the numerator and then there will be the determinant, you will be dividing by the determinant, yeah, there will be some numerator, you can do the algebra, but the point is that the determinant will come in the denominator, and when you execute the multiplication of this matrix with this, the determinant will remain in the denominator. So, the ultimate matrix that you will get, which has 4 terms, will still have the determinant. So, G closed loop will have the determinant in the denominator of all the 4 terms which relate y, the response of y to a change in y set point. Okay. So, therefore, this guy, the determinant, this determinant occurs in all these transfer functions, in the first transfer function, in the in all the 4 transfer functions relating y1, y2 to y1 set point, y2 set point. Therefore, this determinant actually determines the stability of the closed loop multivariable system, because when I change the controller tuning, the determinant changes, therefore, the denominator changes, and therefore, the roots of the denominator change, and as the roots of, and this determinant is common to all the 4 transfer functions 1, 2, 3, 4, right. So, it is so the closed loop multivariable characteristic equation is determinant of I plus GPGC is equal to 0. Okay. Now, let us talk about multivariable tuning. How do we do seesaw tuning? What is the basis of seesaw tuning? Seesaw tuning is what? You take G open loop divided by 1 plus G open loop. Define this as G closed loop, and then what you do is 20 log on base 10 of G closed loop, you define this as LCL or L closed loop, and then what you basically do is adjust Kc such that LCL max is equal to 2 dB. That is what we do, right. Okay. Now, if I take a MIMO system, before I go to the MIMO system, before I go to the multivariable system, please note that by analogy, this GCL is nothing but closed loop characteristic equation minus 1 plus closed loop characteristic equation. See, the closed loop characteristic equation is 1 plus G open loop is equal to 0. 0 minus 1 plus closed loop characteristic equation divided by closed loop characteristic equation, or LHS, left hand side of closed loop characteristic equation. Okay. You can see that the log modulus whose hump I am trying to make sure does not is 2 decibels, that log modulus is coming from closed loop characteristic equation, left hand side of the closed loop characteristic equation minus 1, that is the numerator, and the denominator is the left hand side of the closed loop characteristic equation. Okay. Now, by analogy I define for a MIMO or a multivariable system, I have closed loop characteristic equation is what? Basically determinant of I plus GPGC, this is the closed loop characteristic equation, right, equal to 0. Therefore, by analogy I defined for a multivariable system G closed loop for my multivariable system purely by analogy as minus 1 plus determinant of I plus GPGC divided by determinant of I plus GPGC. If the numerator I call the numerator as W, then this is actually where W by definition is minus 1 plus determinant of I plus GPGC. All right. So, what shall we do now? Okay. So, this is my closed loop multivariable analog of GCL, CISO GCL. Okay. Therefore, LCL multivariable by analogy is 20 log on base 10 of GCL multivariable. And now, what I must do is choose my tuning parameters for the decentralized controllers in a manner such that LCL multivariable max is approximately equal to number of loops times 2 dB, because each loop, so number of loops. So, if it is a 2 by 2 system, I'll tune my multivariable system so that I get an LCL MV multivariable max of 4 dB. If it is 3 loops 6 dB, 4 loops 8 dB. Okay. Now, let us come to tune such that controllers such that this criteria is satisfied, this criteria right here. That is what I want to do. Okay. Insert a new slide. So, here is the systematic procedure, tuning procedure. Okay. Let us say I have got a 2 by example tuning procedure, and as an example I take a 2 by 2 system. So, I have got 2 controllers which we have been looking at. Okay. Obtain KC, for example, Ziegler-Nichols for the first controller, reset time tau I Ziegler-Nichols for the first controller. You also obtain the gain Ziegler-Nichols for the second controller and the tau I, the reset time Ziegler-Nichols for the second controller. Okay. This I can obtain using CISO techniques. These are the individual tuning parameters. Now, the question is, I want to detune both the loops equally. So, what do? I choose a detuning factor. Detuning factor F, and what Lieben recommends is you can detune either, you can keep the tau I the same and detune only the controller gains, and that is what I like to do. Other people detune everything. Okay. So, if you, and F is greater than 1, that is the detuning factor. So, what you then do is adjust F, just a second. What you then do is detune Kc, the controller gain, set Kc1 is equal to Kczn, whatever you had calculated earlier, divided by F, and Kc2 is equal to Kc2 Zn divided by f. So, what I am doing is I am detuning both the tuning parameters, both the tuning, this guy and this guy, from their respective individual Ziegler-Nichols tuning parameters by a factor of f. All right. So, once I have detuned, then I can calculate, because now I know my tuning parameters, I calculate LCL multivariable max, adjust f, adjust the detuning factor such that LCL multivariable max is equal to, for a 2 by 2 system it is actually 4 dB. So, you keep adjusting the, you adjust the controller gains, detune the controller gains by a factor f such that you get a maximum closed loop multivariable log modulus of 4 dB for a 2 by 2 system, 6 dB for a 3 by 3 system, and so on and so forth. So, this is the multivariable decentralized systematic procedure for detuning individual controllers in a interacting multivariable system. It is to derive this that we went through all the trouble and all the theory, etc., etc., etc. All right. So, that is that. Now, last but not least, I want to, until now what we have done is, if I have a 2 by 2 system, I am assuming U1 is controlling Y1, U2 is controlling Y2. A more fundamental question is, should U1 control Y1 or should U1 control Y2 and U2 control Y1? This is the pairing question. What should I pair, U1 Y1 U1, Y2 U2, or Y1 U2, Y2 U1? This is the pairing question. Until now I have been assuming the pairing is fixed, okay. But now the question is, in a multivariable system you also have the choice to choose the pairing. How should I pair? So, there are interaction metrics that are used quite commonly to figure out which pairing gives us favorable interaction. You see, if you remember multivariable systems, the off diagonal terms G21 and G12, and when you are trying to control both Y1 and Y2, they introduce an additional feedback path. And now, if by adjusting my pairing, the G11 and G12, the off diagonal terms can give too much interaction, and for a pairing that has been chosen appropriately, that interaction can be minimized or mitigated. So, pairing can be used in a manner to make sure that the off diagonal interaction terms are as good as possible, so to speak. At the very least, we need techniques to figure out where the off diagonal terms, the interaction is so bad that that particular pairing gives us such a bad interaction that it really makes control difficult. So, how do we, or what metrics do we use to basically reject bad pairings that lead to interaction terms that are very, that are, well, what should I say, I am struggling for a word, but maybe not good. So, we want to characterize interaction, characterize the severity of multivariable interaction, and based on that, those metrics, we should be able to figure out, okay, these pairings the interaction is bad, these pairings the interaction is not so bad. So, these pairings are worth considering, those pairings are worth throwing out the window. Okay. So, for example, if you have a 2 by 2 system, you got two possible pairings, right. What are the two pairings? Y1 U1, Y2 U2, and the other pairing is Y1 U2, y2 u1. Let us say I got a 3 by 3 system. Now I have got how many pairings? I think 6 pairings. Let us see. So, y1 u1, y2 u2, y3 u3, that is one. Then the next one can be, I can flip these guys, I can flip the first two guys. So, what I will have is y1 u2, y2 u1, and then I keep the other guy fixed, y3 u3. Okay, that is number 2. Then I could have y1 u3, y2 u2, and then I could have y3 u1. Okay, then I could also have y1, oh man, this is getting confusing. Then I could also have, okay, let me flip these two, y1 u1, y2 u3, y3 u2. So, 1, 2, 3, 4. y1 u2, y2 u3, y3 u1, y1 u3, y2 u1, y3. So, these are the 6 possible combinations, pairings, couple pairings that are possible, input output pairings, boy girl or input output pairings that are possible. Which one to implement? That is the question. Which one to implement? Should I implement this? 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 Which one gives me favorable multivariable interaction where the off diagonal terms are not as severe, where the interaction, multivariable interaction is not as severe? If the multivariable interaction is not as severe, the need for detuning will not be as severe and I will get better control, right. It is like matching compatibility in couples. Yeah. Okay. Anyway, so that is the question that we are trying to address, and for that there are two indices, two metrics that are very commonly used: Neiderlinski index, and the other one is relative gain array. And what I will do now and finish off is the Neiderlinski index. So, relative gain array. Neiderlinski index is best understood if I use a 2 by 2 example, and these are both steady state metrics extendable to dynamics where you put in transfer functions, but let us just look at the steady state gain. So, let us say I have got a system and I am looking at only the steady state relationship. So, if I make a change in u1, there is a transient in y1, but ultimately y1 ends up changing by so much, the steady state change in y1. I make a change in u1, what is the steady state change in y2? I make a change in u2, what is the steady state change in y2? What is the steady state change in y1? So, that steady state change is essentially the gain given by the gain. Let us say I have got K11, K21, K12. So, let us say I am pairing 1 with 1, 2 with 2. Okay. So, 1 is paired with 1. Yaar, ye kya kiya maine? I am so sorry. Okay, this goes like this and this goes like this. So, what I am doing is I am pairing y1 with u1 and I am pairing y2 with u2. And let us say I do not have a control system, but let us say I am an operator. If I am an operator and I am told, look boss, you have to maintain y1 and y2 at set points. Okay. All right. As an operator, what do? I look at y1, and I see, well, it is not at set point, I may keep adjusting u1 until it goes to set point. Once y1 has gone to set point, then I look at y2 and then I see, oh well, y2 is not at set point, then I keep adjusting u2 until y2 is set point. But because I make a change in u2, the interaction term, the cross term causes y1 to deviate from set point. So, I keep adjusting u1 until y1 is brought to set point. Once I have done that, because u1 has changed, I keep y2 would have deviated. So, I keep adjusting u2 to bring y2. I keep doing it again and again and again and again. Hopefully, if I have done it sufficient number of times, y1 and y2 will get close enough, if not exactly, to their set point. So, that is the basic thinking that I will apply to derive Neiderlinski index. So, let us say everything is at set point. So, set point is 0. So, y1 is at 0, y2 is at 0, u1 is at 0, u2 is at 0. Everything is at set point, as is at steady state. I am where I want to be. Now, let us say a disturbance comes in, and let us say the magnitude of this disturbance is 1 and everything is getting added up. Because the disturbance came in, now y1 has gone to 1. If y1 has gone to 1, what should I do to u1 so that this signal becomes minus 1? Then 1 minus 1 will bring this to 0, yes or no? So, to repeat, I was at steady state, a disturbance came, caused y1 to deviate. I as an operator see that, oh, y1 has deviated. So, then what I do is I make u1 minus 1 by k11. If I have made u1 minus 1 by k11 and I wait long enough for the transients to pan out, what I will find is u1 has been made minus 1 by k11, and therefore, this signal is minus 1, and now minus 1 plus 1 will bring y1 back to 0. However, when I have changed u1, this signal becomes k21 by k11 negative sign, yeah, and therefore, y2 goes to minus k21 by k11. In order to then I say, oh, y2 has deviated, y1 is at set point, y2 has deviated. What should I do to u2 in order to bring y2 to set point? Well, if I change u2 to minus k21 by k11 k22, then this signal after multiplication by k22 will become minus k21 by k11 plus. So, this will become plus, and once this has become plus, these two terms cancel out. Because these two terms cancel out, y2 goes back to 0. Even as y2 has gone back to 0, now u2 has changed, and because u2 has changed, this term will become k12 k21 divided by k11 k22, yeah, and therefore, now y1 will go to plus k11 k21 divided by k11 k22. So, now I have brought y2 to set point, but y1 has deviated. In order to bring y1, I will again make a change. That change will again affect y2, and then once y2 is affected, I will again make a change to u2, and that change will again make a change to y1. So, you see, if I keep doing this again and again and again, after one circle, what I find is that if I look at u1 after disturbance came in, the first value that I gave it was minus 1 by k11. and then y1 deviated after I had done adjustments to u2 by k11, k21, k11, k22. In order to bring this to 0, I will have to make a change of minus 1 by k11 times whatever was the deviation, k11, k21, k11, k22, yeah. And then if I do it again, what I will get is k12, k22 whole square plus and so on so forth. So, basically what I am saying is u1 would change by an infinite series. If I keep it doing again and again and again, it will change by 1 k12 k21 divided by k11 k22 plus k12 k21 divided by k11 k22 whole square plus and so on so forth. This will be the infinite series. Okay. u1 has to change by this guy 1 plus k12 k21 divided by k11 k22 plus and k12 k22 divided by k11 k22 whole square plus and so on so forth, an infinite series. This infinite series will converge to a finite value if and only if k12 k21 series converges for converges to a finite value, converges to a finite value for this multiplication factor being less than 1. On the other hand, if this multiplication factor is greater than 1, series diverges to infinity for this guy, yes or no? All right. Therefore, if this condition is satisfied, guaranteed the interaction is so bad that the if I am trying to control both y1 and y2 at set point, if I am trying to maintain both y1 and y2 at set point, guaranteed the inputs will blow up, the inputs will blow up to infinity. Okay. u1 will blow up to infinity, u2 will blow to infinity, plus infinity or minus infinity. The change would be the magnitude of the change in the inputs required to maintain both y1 and y2 is actually blows up to infinity. All right. So, if this is true, then you have instability. In fact, it is called integral instability. And why do we call it integral instability? Integral action causes 0 offset. So, if you are using a PI controller in order to maintain things at set point to get 0 offset, then integral action is in there, and if integral action is in there and you are trying to control to maintain the process outputs at set point, and if this condition is satisfied, you get instability, more specifically integral instability, integral indicating that we are trying to maintain both y1 and y2 at set point. All right. So, what that means is if 1 minus k12 k21 divided by k11 k22 is less than 0, this implies integral instability. And what that means is, if I solve this further, k11 k22 minus k12 k21 divided by k11 k22 is less than 0 implies guaranteed integral instability. Yeah. Now, if you look at the input output relationship, what I had was I was trying to do y1 y2 and y1 is being controlled using u1. So, this is actually k11 k12 k21 k22 into u1 u2. Yeah. So, if you look at this metric, what is it? It is actually the determinant of the gain matrix, the steady state open loop gain matrix divided by the diagonal terms. Yeah. So, we define Neiderlinski index as equal to determinant of the gain matrix for the pairing that you are recommending or that you are testing it for the pairing being tested, divided by the product of diagonal terms. This is called the Neiderlinski index, and if this Neiderlinski index is less than 0, then you have guaranteed integral instability. What that means is that the interaction terms are so bad that if you try and control y1 at set point and y2 at set point, if you try to control the outputs at set point, guaranteed things will blow up. Okay. Continuing with this 2 by 2 system, let us say right now I got the Neiderlinski index for the pairing y1 u1 y2 u2, and the Neiderlinski index was k11 k22 minus k12 k21 divided by k11 k22. Let us say I do a different pairing. Let us say I say y1 is paired with u2 and y2 is paired with u1. This is the other pairing. In this case, what you will have is, you still write the same thing. However, now what I am doing is y1 is being controlled using u2. So, what I will do is y1 is being paired with u2 and u1 is controlling, is trying to maintain y1. So, in this case what I will get is, this guy would be k on 1 of 2, k on 1 of 1, k on 2 of 2 and k on 2 of 1. Do you see that the gain matrix earlier for y11 y1 u1 y2 u2 pairing was, do you see that the columns have been shifted? I have just interchanged the columns. Yeah. So, interchanging of the columns of the gain matrix corresponds to flipping the pairing, and for this guy the Neiderlinski, for this pairing the Neiderlinski index would be determinant, and the determinant is actually k12 times k21 minus k22 by k11 divided by k11 k22 divided by diagonal terms. So, k12 k21. Do you see that the sign of the determinant has changed, and therefore, usually for 2 by 2 system, one of the pairings would give you a positive Neiderlinski index, the other pairing is likely to give you a negative Neiderlinski index, and what that means is one of the pairings can be integrally stable, the other pairing is guaranteed to be integrally unstable. And so, what am I trying to say? What I am trying to say is, if you have a pairing question and you want to use Neiderlinski index to figure out which pairings give you very severe interaction, then what you do is tabulate all possible pairings, all possible pairings, calculate Neiderlinski index for them, for each. Ni less than 0, these are bad pairings. Ni Neiderlinski index close to 0 but greater than 0, approximately equal to but greater than 0, these are, this cannot be used, these are poor pairings. And Neiderlinski index close to 1, these imply mild interaction, mild interaction. These are the pairings which where the Neiderlinski index is close to 1. That means, yeah, if you look at the Neiderlinski index, and if the Neiderlinski index is exactly 1, what that means is numerator is equal to denominator, then you will get cancellation and you will get 1. What that means is, if numerator is equal to denominator, denominator is k11 k22, numerator is k11 k22 minus the product of the off diagonal terms. What that means is the product of the off diagonal terms is 0, that means at least one of the interaction terms, either k12 or k21 is 0, at least one or both. What that means is, at least from the steady state perspective, there is, you know, the additional feedback path introduced due to multivariable action, multivariable interaction is broken because one of the off diagonal terms is 0. Yeah. So, Neiderlinski index close to 1, those pairings are worthy of further consideration. Neiderlinski index, pairings that give Neiderlinski index less than 0 are guaranteed to be unstable. So, those pairings you do not need to think about at all. Okay. Now, one thing that I want to point out is Neiderlinski index is a, you know, necessary but not sufficient condition for stability, in the sense that if Neiderlinski index is less than 0, you get guaranteed instability. If Neiderlinski index for a pairing is greater than 0, well, there is no guarantees, and I mean this, you know, I mean even if you have a single input single output system, you can always screw up the tuning so that the closed loop system is unstable. So, Neiderlinski index is essentially a necessary but not sufficient condition for integral stability, integral stability. So, what we are saying is that if Neiderlinski index is less than 0, guaranteed instability. If it is greater than 0, well, you may still get instability depending on how you tuned your controllers. Okay. So, that is that. I think it is a good time to end. Thank you very much.